We're back, I think. Yeah, we are back. So, same board as before. Last time we did the USB connectors, we wired them up. Now we're going to do the main circuit for the board. So, visually, it's really good on the schematic to go to a different location. If you want to be really clean on your schematic too, sometimes what you can do is if you're trying to keep everything on one sheet, well, you know what? Let's save first. All right, we got a license issue. Look at that. See what happened? I can't save this because it says it's not supported by the current license. So, this is the problem people have. And switch Wi-Fi. Oh. Okay. So there's 4 of you right now at 3:33 p.m. on Tuesday using this. So, well, there's one of me, I guess. So I had to reconnect the license server. I don't know why it died. That was a little weird. And then we'll do. Oh. Yeah, I should have saved before I left. And as I said before, we set these air wires because the ground's not wired up. And I'm going to show you how to do a ground plane later on. So, but for now, I'm just going to leave the grounds. So we have our 5 volts here and grounds we're not going to worry about. Let's go back to our sheet. Try to do what I was doing. So if we want to be a little more clean when we're doing a schematic design, one thing we can do is we can just kind of place lines here to clean this up. So we can place lines and we can, put a little box around these. Something like the and what that's going to do is just visually as we add more stuff to our design, it's going to show that it's just our eye is going to be able to compartmentalize this and say, okay, all this stuff, even though these all look different, this is all USB connectors, and this is a handy tool. It's nice to be able to do this not only just to make it pretty for the sake of being pretty. Doing things like this is a good way to prevent you from tricking your eye. So complexity, things being a different design, things being a different style like this is normally very bad because it's your eye is looking for patterns and it sees these differences and it automatically is going to assume something's weird. And so visually sectioning these off as their own thing is a nice way to just trick your brain into thinking, okay, these are all kind of related. These are all the same. I don't have to, if I'm looking at something else, I don't need to worry about this stuff that's here. So, and the benefit of that is if somebody else is looking at the schematic, they're more likely to be able to identify real mistakes. They're not spending as much time visually, mentally focusing on things that aren't productive. They're able to sort of look at your design and see, because it's presented in a way that's clear, what's clearly wrong about it. So, all right, so I'm just going to start off by just throwing down some op amps. And I might kind of have to do some work here that's just a little quick. So I might have to kind of shut up and have you fast forward at one point in time. But let's go back to our component. And I'm going to use, my design has 8 op amps, I believe. So I'm going to use this quad op amp. And as I mentioned before, when we're doing quad op amps, I like to just, I know there's 4 per package. I know I'm going to need a total of 8. I'm just going to dump all 4 op amps right now. So now I know this is one physical op amp. And for me, I kind of like to do the second physical op amp sort of down like this. And the benefit of this is it makes sure that Altium knows, for now, when these things are set up like this, if I annotate this, it's going to annotate them in order. And with op amps like this, when we got multiple parts on one package, I might even just want to annotate it right now. If I annotate it right now, it's going to assign the particular physical package to each one of these symbols. And then I can use that to know, okay, this collection of op amps is all in this package. I'm going to keep it all together. This one's all in here. And we can shuffle around the op amps after they're labeled and certified as part of the package. So I'm just going to annotate slightly. Okay, so now if we zoom in, we know this is U1, A, B, C, D. So all four of these parts are on one physical chip, and all four of these parts are on one physical chip. And we can keep that in mind as we're moving these around to different parts. We can sort of decide how we want to structure it. I'm just going to just do the design. But one thing that's weirding me out here is op amp. Right? We got pin 4 and 11. So pin 4 is going to be, this is a 14-pin package. Pin 4 is going to be sort of on the left side in the middle. Pin 11 is going to be on the right side in the middle. I want to make sure before I get too far here, which one of these is ground and which one of these is power. So to do that, one thing we can do if this is properly, if I properly stole this from parts library here, I'm a little worried this might not be the right part. So I don't get the, well, what I'm going to do is I'm going to go back to our project. This part number, this is the part we got. You verify that. So we have the parts physically here. This is a really important step to actually physically verify this right. 49431 ND, and this is 2 ND. I don't know the difference, but this part is 1,000 op amps here. So check this. I don't know why, whenever I search for stuff from DigiKey, it takes me to like digikey.at. I don't even know what .at is. What is that? What country is AT? Ataturk? No, that's a person. That's the Turkish dude. This is gonna drive me nuts. This is the time where normally I'd start going down a Google rabbit hole here. Let's just verify this. Okay, so it looks like pin 4 is VCC. So that should be our high voltage. Make sure we're not going crazy. I didn't get much sleep last night, so. Yeah, so these are high voltage. So pin 4 needs to be our high voltage. So just as a sanity check here, and I like to even after the board is all laid out, I like to go back and just verify that everything seems reasonable. So we had, so these are flipped. The non-inverting's 3, the inverting's 2, but then the non-inverting's 5, and then it's 6. So I just like to sanity check. But pin 4 has to be 5 volts. So let's go back. Pin 4 is 5 volts. So instead of renaming one, let's do our shift grab. And on this particular op amp part, only the first one, only op amp 1 has the power rails. Some op amps, every single part that you place has its own power rails, which are connected to the same pins. You got to be really careful with that because you got to make sure that you only connect the same signal to one of them. Sometimes if you connect a different voltage to 2 op amps that are on the same physical package, Altium will interpret that as you wanted those two voltage rails connected. So Altium will interpret that as connecting two voltage sources to the same wire, which won't necessarily throw an error. It might, sometimes it'll say like you double labeled that signal, but it might not throw an error, so you got to be careful. Okay, that looks good. I am going to populate the first part of my circuit. Feel free to speed this up if you want along the way. Okay, in case you're fast forwarding it or skipping through it. So one thing I want to talk about. So these op amps are all positive terminal up. So if you want to make them look more like a normal op amp, you gotta flip them. We normally have the negative terminal at the top. I did that for the op amp that I'm going to use, the difference amplifier. I didn't do it for this one because of the power rails. I just wanted to keep the power rails where they are, high voltage on top, ground on the bottom. So this is going to be the first op amp that we have in our design, and So just note the design is a little bit backwards. Hold on, let me pause the recording real quick. Okay, I don't know where I was when I left. That was kind of a quite the pause. Okay, but so this is our first op amp in the circuit. So this is the resistor that's going to control the flow of current. I'm not quite sure what value I want there yet. This is going to be the divider that gives the voltage that it sets the other one to cause the current to flow. So the feedback path through our battery is going to have to be here. So what I'm going to do is I haven't placed values here yet, but I'm going to place the battery here. Go to components. And so we have a 24 millimeter coin cell. So remember, we want the positive end of the battery, we want current flowing out of the op amp into the positive end of the battery. And I am going to also do the 20 millimeter. I'll show you this. So you might say, well, what the heck? These are both in parallel now. Is that going to work? The idea here is we have two different size battery holders. We're probably only going to be putting a battery in once. I think what I'll do is I'm going to put one battery holder on one side of the board. Sorry, one battery holder on the other side of the board. And so then you can insert, if you want to insert a 2032, if you want to insert a 2477 or 2450, you can insert it on either side and it'll accept it. But it gives you the choice. So probably one of these is going to be open circuit and the other one's going to have a battery in it. It's going to work the same either way. So we got to be just really careful not to wire these upside down. And I'll be checking your circuits and I'll try to make sure that's not the case, but we'll do what we can. So what voltage do I want to have here? This is another step that I want to go through. I want to talk about 1% resistors. So let's say I'm trying to do a, let's say I'm trying to make this, I'll do 0.4 volts. I'll do 0.4 volts as my set point here. And because I think other people are doing something different. So I'll say I want 0.4 volts here. And I want, so we're going to generate, we got 5 volts up here. Ground down here. So what values do I pick for this to get point? So 5 volts, we're trying to get down to 0.4-ish. So this is going to be ballpark 1/11th. So we could do like a 10K and 100K-ish. So 10K and 100K is 4, 5. Nine K is close. 2. Could actually calculate it. Could actually do the algebra here. I'm just going to ballpark it. So it's going to be a little bit less than 9. So if we have 100K up top, I know that's a part I can get. So to generate 0.4 volts here, we need to have a resistor value that's slightly less than 9K. So how do we determine what resistor values we can actually use? We can go to the 1K resistor table, which I have here. So this is the 1K resistor table. Oh. So this tells us all the, to 3 digits of significance, it tells us all the values we'd have for resistors. And we can do any fraction of 10 within here. So the values we have are 10 ohms to 10 mega ohms. So if we want something, let's say slightly less than 9, we could do an 8.98K resistor. We could also do an 8.87K resistor. So let's try, if we do 8.87 divided by 108.87 times 5, we get 0.407. Yeah, maybe let's try 8.76. So 8.76 divided by 108.76. Well, maybe a little smaller. 866. 8.66. 108.66. Yeah. 866 gives us 0.398 volts. 876 exactly. So if we do 876, we get 0.403 volts. And if we do 8.66 and 100K, we get 0.3985. So that one's closer. So 0.866 is going to be closer. Now, when you're playing with these resistor values, trying to get something close to the ratio you want, you can also play with these on the other side. So instead of a 100K resistor, I could have a 101K resistor. So sometimes it works out better if you do 101K. If we did 101K and 0.8876, it might actually give us a better ratio. I'm kind of curious. So we do 8.76 and 10976. Yeah, so that gives us 0.399. So if we did a 101K and 876, that gets us very close to our ratio. Someone just got to my house. So let's do that. So and you've got to be careful though, because you can only do that when you know you have the resistors. So and in this case though, even if we didn't have the resistors, we could choose a different ratio after the fact. The footprints are the same. But for the design, when we're limited to these resistor values, we can't get it exact. You don't get to pick an exact resistance that you want. If you need it to be precise, absolutely positively need it to be precise, despite this 1% issue, you can also put a small potentiometer in there. So we could have done like 100K on one side and 7K on the other side, and put a 2K potentiometer in the middle there. So then we could adjust the potentiometer to dial it in exactly. That's one option. But so what did I say? 8.76K and 101K. So it's important also when you do these schematics, you use actual resistor values that you can get. So make sure you use the table, the 1% table. You can see the website I go to here. So 8.7, if I go crazy here. Okay. This one is 101K. Okay. So now this should generate 0.4 volt, so 0.399 volts. So that's about as close as we're going to get here. And sometimes we like to you can place a label there, something to remind yourself if you're curious, especially when we're using a divider to generate voltage values. Sometimes it's handy to just put some text here that just says like 0.3991. So that's not actually like a net label, it's just a a visual reminder for us that, hey, you know, FYI, that's the value there. And actually, it's not, when I do that, it covers the wire. So this is a time when it might be good to have the grid change. That's better. Okay, so 0.4 volts. Okay, so I am gonna have to play some games down here, so I kind of want to give myself some space. If I hold control and drag, it maintains the wire. That's another thing to remember. Actually, I probably want to give this some space too, because I'm gonna have to do some work in here. Okay, so another thing, so I have these 4 op amps here, and I've done my first driving op amp, and then my second, this is going to be the difference amplifier, but I wanted to put buffers in between. Why did I use these ones? Why didn't I make this a buffer and this a buffer and then this the difference amplifier? Well, think about as we move around this chip. So as we move around this chip, this op amp is pins 1, 2, 3, and 4. So that's going to be the top left corner of the chip. The next op amp is going to be pins going clockwise. The next op amp is going to be the pins on the other side of the chip, the highest number chip. So if I want to have the circuit built on the top left corner of the chip, and then I want to have the buffer on the top right side of the chip be one side of the buffer, and the buffer on the bottom right side of the chip be the other one, and then curve back around to the bottom left corner of the chip. I want this op amp to be the bottom left corner, you know. So what I'm doing is I'm designing right now, knowing that I'm going to have to populate these parts and connect them around. So I'm trying to sort of do them in order so it wraps around the chip. It doesn't have to be in this order. It probably would have worked out fine either way. But if the signal here had to go directly to 2 buffers, I want them to be in order adjacent to it. I could have wrapped it around the other way. That probably would have worked just fine. But sometimes a little bit of design consideration when you're picking which op amp you're using can save you a lot of effort later, especially when it comes to effort that prevents you from having to like do a bunch of through holes and route a bunch of stuff around crazy. Sometimes just choosing a different op amp can make a big difference. Okay, so back to building, back to probably, to me, shutting up for a sec. So I've got the buffers set up. They're going into the difference amplifier. I have the high side, the positive side going into the positive input. The low side of the battery going into the negative input. The question now is, so now I have a signal out, and this signal is reference to ground. It's the voltage across my battery. So there's three different conditions we have. We have when the battery is under 3 volts, when the battery is between 3 volts and 4.2 volts, and when the battery hits 4.2 volts. So, oh, we gotta pause again, sorry. Okay. So, we got a buffered. I'm gonna have to do some stuff here. Okay. Oh, I added the jump. So just note that was a setting. You can go back in the video and see where I changed that setting. Normally, if we start to get all spaghetti like this, that's usually when we like to start labeling signals instead of just running wires everywhere. And we'll probably label a signal here later on just for cleanliness. But okay, so now we got to think about how we want to turn on this current. So we want to have, we got 0.4 volts here as a constant voltage. If we want that 0.4 volts to translate to 2 volts, so sorry, to 2 milliamps, oh, my calculator app crashed. So 2 volts, 2.4 volts. It's going to be a 200 ohm resistor. We want to have work. So now I just entered 200 here. Do I actually have 200? No. Yes, I do. I have 200. So we're good. We actually have a 200 ohm. Another thing to think when you're using these resistors for current limiting, you got to check power. Surface mount resistors are usually 1/32 of a watt. I'm pretty sure we're not going to be anywhere close to that. But when you're doing a design, it can be really easy. If this had been more current and we had just chosen a resistor value that was fairly small or fairly big, we have to be really careful. So power is I squared R. So in this case, the power is going to be 200 times 0.002. In this case, our power is going to be 800 microwatts through that resistor, so that should be fine. But surface mount, you got to be careful. They're using, the large through-hole resistors are usually going to be 1/4 watt, maybe 1/10 watt. But these surface mount ones are much smaller. They can't dissipate heat that well, so they're usually 1/32 watt. And there are ways you can improve it if you know that's going to be the case. There's techniques you can do, like putting a big metal pad on the sides of the resistor to help dissipate heat, or just using a bigger resistor. But you got to be careful. A lot of times this resistor here is the one that people do the wrong size, and their design comes back and it explodes or melts down or gets really hot. So something in general when doing design and using a shunt resistor, so you have a lot of current flowing through anything, make sure to check the power for that. The rest of this should be fine. We shouldn't have too much power here. So, okay, so we're gonna have to put a transistor here. So I'm gonna go back and look in the project document. Forgot the name of the one I told you. So NMOS, N-channel MOSFET, BSS 138. BSS 138. Right here. So be careful when we place this, right? So we have, always rely on the body diode. So if you're using a transistor to to block current, well, I gotta set my grid. If we're using a transistor to block current, we want to make sure, if we're not sure about, source, drain, collector, emitter, whatever, look at the body diode. In this case, what direction does it have to be if we're trying to block current flowing through it? It's got to be oriented like this. A lot of students take this, and they rotate it, and they put it in like this, and then if we had it in here, this would be backwards. There'd be no way to turn off the flow of current between pins 2 and 3 here because of that body diode. So I like to rely on the body diode as a nice visual reference here. I don't looks like it's going to be too close, so. Okay, so we got that for now. It looks to me like I'm probably going to want to space this out a little bit more. Didn't pay too much attention to where these things are. So, we could hold down control, move these around if we want, kind of align them. So, feel free to move in here, hold down control, move this around. Yeah, that might be better. That might be better. We can even okay, so we want this signal to turn on so we want this to be on, oh, wait, all the time. This is our default. This is our default current. Yeah, what am I doing? I'm still going to keep this transistor around, but no, this is our default current. This is our always current. It's our always, for now, current. No, I'm not. I'm totally designing this. Totally designing this. I did this on paper, and now I completely flipped it around backwards here. We'll still do that. Let's keep that. Yeah, we're gonna do a couple things here. We'll keep that. Okay, so 200 ohms will give us 2 milliamps. What resistance do we need to give ourselves 10 milliamps? So with 0.4 volts, the resistance we need to give 10 milliamps is going to be we want it to be 40. I'm really sorry for the interruption. It's hard to get these videos done. So, we'll do it now though. So, okay, so we need a total of 400 ohms here. Sorry, 40 ohms to get 10. So the question is, we're gonna have to put a resistor in parallel with this once we hit 40. Once we hit 40. Yeah. We got to put a resistor in parallel with this once we hit 40 ohms. Sorry, once we hit 3 volts. So what resistor in parallel with a 200 becomes a 40? So 1 over x plus 1 over 200 equals 1 over 40. So it's 1 over 40 minus 1 over 200. $50. So, and now for this gate, what I'm going to do is I'm just going to label this. So I'm going to give this a net label. Put the net label here. Click it. So what this is it's giving a name to this signal, and that means that anywhere else that I put this net label, any other wire that I give this signal to is going to be connected here. Even if we don't physically show a wire, they're labeled the same, they're going to be connected. So in this case, I want to control the gate of this transistor, and I want to control it when we've hit 3 volts. So I'm gonna call this 3V big. A little weird how little ones showing up there. Okay, so now I can control this transistor with a 3-volt signal. I'm gonna do this later though. So right now, so there's one more transistor I'm gonna add that's gonna be over here. Actually, another signal. I might just want to stop and do some, with what we got right now, I'm going to do some board design before we get too far. So make sure all the values are good. Looks good. Design. And I'll probably have to come back and do another video of this tomorrow. So let's do. Those errors occurred during compilation. Go back and just see what those were. Okay. Net BT01 contains output pin and high Z pin objects. Oh, and high impedance pin object. Yeah. So what it doesn't like is that this is an output, and it's connected to a high impedance, and that's basically what this is labeled an output as a way of sort of preventing you from making errors, and that output should be connected to inputs. You shouldn't have 2 outputs connected. And the inputs of this are high impedance, which matter for things like noise sometimes. So what's happening here is it's warning us. It's saying that we have an current output, an output pin connected to a high impedance pin. That could be an issue. It's not an issue in this case. We know it's not an issue. It's okay to connect the output to these pins of these op amps, but it's just warning us that it could be an issue. So it's okay. We can ignore this. We don't have to worry about it. It's going to be fine. Okay, so you'll notice we have this U2 op amp is unused. We have these massive coin cells. This thing is probably going to end up having to be big. And we have this op amp here. I'm probably going to start with this op amp here, and I'm just going to assemble this thing, get it all put in place, so that we got this one for the most part done. There's probably going to be some other stuff we have to fiddle with it but for now. So whenever I see a situation like this, I go back to my schematic. So I have a bunch of these things I got to wire to this thing. All this stuff has to be wired. Okay. Transistor has to be wired to it. So how am I going to do this? I like to start assembling this by looking at going back to the schematic. So this is my transistor pins 2, 3, 4. Oh, sorry, pins 2, 3, 1. Looking at that is pins 2, 3, 1. So that transistor is going to be here. So what resistors have to be clustered around there? Well, let's see, 6, 8, 10, 11, and the transistor. 6, 8, 10, 11, 6, 8, 10, 11, transistor. 8, oh, 8, 6, 11, and the transistor. Okay. So now those are the ones we know need to be nearby here. So let's just see how they connect. So I got a ground here. I got a ground on the transistor too. Go back a little bit and let's think about how we wire this if we had it on a breadboard. So I'd probably connect R6 and R8 to do the divider. Let's do that. Give ourselves a little space. R6 and R8. Slide these down there, so we might just want it upside down. That R6 is going to tie into there. And then we're going to have these resistors connected, both these resistors connected to pin 2. Go back and see. Divider, and we're going to have to get this around it. Oh, let's switch these. And so we don't have to be high density. We don't have to kill ourselves here. We can space this out a little bit. Transistor. Well, eventually it'll have something tied here. It's gonna have to come from somewhere else. You know. The thing is, I might have done something bad because I'm gonna have to build. I put both circuits that got a lot of stuff on this side of the chip. That could have been a design mistake. And we can always go back. Nothing's ever gone forever. Okay. The one thing is I don't like the size of these silk screens. So what I'm gonna do is I'm gonna click this and I'm gonna right click and go find similar objects, text same, and I'm gonna say text. So that's selected all of these annotations here. I'm just going to shrink these things. They're too big. So we can make these 30 mil. And if we do that, we want to set the stroke width to 6 mil. And that's about the smallest we can, let's do 35. 35 mil, 6 mil width is about the smallest we can get these. But it's going to kind of just, not make them so ridiculously big. Okay, this looks like it's going to be fairly easy to route now. So the BT1 is going to have to find its way through. It's okay, we might have to do a through hole or something. Actually, we can snake it through this resistor if we want to be daring. We might want to be daring. Well, I'll get to that later. Let's populate the other chip here. The other chip here was down here, so it's 7, 5, 9, 12. All the ones. Okay. Okay. So let's fix this out. We don't have to be ridiculous. And then let's route. I'm just getting these out of the way for now. Now these are all signals. These don't carry a lot of current, so we don't have to be too worried about the size of these. These could be pretty tiny, actually. I might set these to smaller than that. 8 mil should be fine. Smallest thing goes 6 mil. I don't like to go. I don't like to go all the way to 6 mil if I don't have to. So I feel like I'm going to end up moving now. But you see, this routing is going pretty well right now. It's going well because we were deliberate about, we were kind of thoughtful about where we wanted to put this stuff. We can snake this through here. This is a little. Usually, you got to be careful with these because, you can have issues, but better than doing a through hole. I'm going to take the 5V out just for now. Grounds, we don't, eventually the grounds we're going to use a ground plane. Don't care too much about these right now. Now, this signal here, I'm going to snake this grid a little bit less. This thing, I'm going to snake it. I'm going to snake this through here. The reason I'm snaking it through here is because this signal pin is going to have to be a signal that comes from somewhere else. So I'd rather kind of keep it on the outside. Okay, so we got to get this R6 one. Okay, yeah, we get this one. One. Did I want to do that? Snake it through there. That's probably dumb. I mean, I probably should come back and just do a through hole, but I don't like through holes. We got ground and ground. I'm not too worried about the grounds right now. We'll get them in the end. But okay. Oh, and also, yeah, we got these our buffers here. We don't actually need. Oh, look at that. Yeah, because we snaked that thing through there. Now that guy won't go. Good. Okay, the batteries we'll worry about later. Okay. We just did some tricks. This is looking a little ugly. This is starting to look a little gnarly. So sometimes I'll come back and I'll try to clean these up a little bit. So. Okay. I'm just kind of cleaned it up a little, just tidied it up a little bit. I think good. So as a general rule, you don't want big loops. Big loops are susceptible to noise, so you kind of want to keep your loops tight if possible. This is pretty good. This is a pretty compact circuit right now. So I'm going to call this good for right now. I got to go home and get some dinner for my family, and then I will post another video tomorrow.